Okay, this is exam 3 for Physics 102, spring 2011. It says a concave spherical mirror has a radius of curvature of 20 centimeters. That means that the focal length is going to be half that value, and so the focal length is 10 centimeters, and it's a concave mirror, so it has a positive focal length. The object is located at 20 centimeters. That's our p-value. What is the magnification? Well, the magnification is minus q over p, so we need to solve for q. 1 over f is 1 over q plus 1 over p. So q then is 1 over f minus 1 over p to the negative 1. Let's see, that is 1 over 10 minus 1 over 20 to the negative 1. That's 2 over 20 minus 1 over 20. The inverse of that is just 20. So q is 20, so the magnification is negative 20 over p, which is 20. So the answer is D, negative 1. A bank uses a mirror for security purposes. That should tell you right off that it's a convex mirror, because that is a convex mirror. A person stands 10 meters in front of the mirror. That's p equal 10. And the image is 6.7 behind the mirror. So it's negative 6.7. What is the focal length? The focal length is 1 over p plus 1 over q. The inverse of that, that's from this same equation. That is 1 over 10 plus 1 over negative 6.7 to the negative 1. That gives me negative 20 meters. So the answer is A for number 2. A convex lens has a focal length of 20 centimeters. That's a lens like this, a converging or convex. The focal length is here. The object is located 10 centimeters to the left of the lens. Which of these describes the image? Well, it's going to produce a virtual upright image. So that's here or here. All right, but if it's virtual, it has to be on the same side as the object. So that means that it has to be, what is this, E, because it's to the left of the lens. So it's not A, because a virtual image with a lens is on the same side as the object. Consider the following two-lens system. What is the magnification of the final image? Okay, well first, this is P1. Then we want to solve for Q1. That's 1 over F1 minus 1 over P1 to the negative 1. It's 1 over 10 minus 1 over 20 to the negative 1. It's a calculation we've already done. So it's 20 centimeters. And so the first magnification, M1, is negative q over p. That's negative 20 over 20, which is negative 1. Now we want to consider the second lens. Now this image is 20 centimeters to the right. So it's right here. This distance, which is Q1, is 20 centimeters. And now this distance, which is P2, is equal to 60 minus 20, which is 40 centimeters. So P2 is 40. I want to solve for Q2. That's 1 over F2 minus 1 over P2 to the negative 1. That's 1 over 20 minus 1 over 40 to the negative 1. Let's see, that's 2 over 40 minus 1 over 40, so that gives me 40 centimeters for Q2. So my M2 is negative Q2, which is 40 over P2, which is also 40. So that is negative 1. Negative 1 times negative 1 is just 1. For the total is equal to M1, M2, which is just equal to positive 1. For number 4, then, that is C. This figure shows a mirror along with an object and the image the mirror forms. What kind of mirror has produced this image? Let's see, I changed this so that the image was inverted. Alright, and all you really need to know then is that the image is a real image, right, because it's on the same side as the object. And the only mirror that produces a real image is a concave mirror. That's a mirror that's like this. What is the magnification of a flat mirror? It's 1. Because P is equal to negative Q, the magnification is positive 1. Most cameras have an aperture to block the outer edges of the lens. That's to reduce spherical aberration. That's C. Which of these physical phenomena are the cause of mirage? That is C, a refraction. Two slits are separated by a distance of 5 millimeters. That is D, 5 times 10 to the minus 3 meters. Light of wavelength 522 nanometers, that's times 10 to the minus 9, is incident on the two slits on a screen 12.2 meters away. What is the distance from the central maximum to the third bright fringe? That's m equal 3. D sine theta, this is double slit, is equal to m lambda. This is to the bright spots. I first want to find theta. That is the inverse sine of m lambda over d. Let's see, m is 3. Lambda is 522 times 10 to the minus 9 divided by d, which is 5 times 10 to the minus 3. Inverse sine. I get 0.018 degrees for theta, but I want to know the distance. That is y equals L tan theta, where L is 12.2, so I take the tan of that angle times 12.2, and I get 3.8 times 10 to the minus 3 meters. That is 3.8 millimeters, so that is B. Diffraction gradient has 12,000 lines per centimeter. That means if I want to find D, I take the inverse of that, and that's going to be in centimeters. That gives me 8.33 times 10 to the minus 5 centimeters, which is 8.3 times 10 to the minus 7 meters. Light of wavelength 436 nanometers is incident. How many bright spots are on the screen? So I'm looking for the maximum number of orders. That means that theta is going to equal 90. And so d sine theta is equal to m lambda. That is d, the sine of 90 is just 1, is equal to m lambda. I want to solve for m. It's just lambda over d. If I do this lambda over d, let's see, lambda is 436, e to the minus 9. Oh, I'm sorry, this is not lambda over d. Okay, no, this is solving for m is d over lambda. Okay, so it's 8.3 times 10 to the minus 7 divided by 436 e to the minus 9, and that gives me 1.9. That means that there is only one order. Alright, so including the central maximum, this is what it's going to look like. So that means I'm going to have 3 spots. This is my m equal 1. Since it doesn't go up to 2, I just round it down to 1. Alright, so that was answer A for 10. Alright, the green line of gaseous murky at 546. So lambda is 546 times 10 to the minus 9 meters. Falls on a single slit, the fourth dark fringe. And remember, with a single slit, the order number is for the dark fringe is 4. Theta is 0.092 degrees. What is the slit width? It's a pretty simple problem. I just say A sine theta equal m lambda. I'm solving for A. It's just m lambda over sine theta. That is 4 times lambda over sine of 0.092. I get 1.4 times 10 to the minus 3 meters. That is 1.4 millimeters, which is A. Consider these two waves. What type of interference occurs when the two waves combines? Peaks line up with troughs, so that's destructive interference, number 12. Previous figure, by what amount are the two waves out of phase? Alright, well, for destructive interference, it has to be a half of a wavelength out of phase. I can think about it, this wave, or this is a full wavelength, And so that means that if I were to take this back a half a wavelength, if I were to take this part back, they would be in phase, so it's offset by a half of a wavelength. LIGO as an observatory is based on which of these devices? It's essentially a great big Michelson interferometer, so the answer is A. In fact, LIGO stands for the Laser Interferometric Gravitational Observatory. Double slit experiment, what is the wavelength of when the wavelength of the light is increased, what happens to the interference? Well, for double slit, d sine theta equals m lambda. So that means if lambda goes up, theta also goes up, so that means that it spreads out. Single slit experiment, what path difference from each slit traveled to give a maximum, I changed this in class, at the indicated position? Well, this is 0 wavelengths, this is 1/2, this is 1, 1.5, this is 2. So right here we have a 1 wavelength difference, that is D. Okay, waves from this radio station of wavelength 600 meters. Arrive at a home receiver a distance 50 kilometers away. This is given, but you don't really need that number. The transmitter by 2 paths. One is a direct path, and the second by reflection. What is the minimum distance so you have destructive interference at the location of the listener? We had a similar concept test question like this, where we had the waves that travel 2 and 3 meters, and they had a wavelength of 1 meter. Well, in this case, your wavelength is 600 meters. It's a long wavelength radio wave, and we want destructive interference to occur at this point. So that means that the path length difference for destructive interference, the path length difference has to equal a half of a wavelength, which in this case is, half of 600, which is 300 meters. So that the black wave, or the ray that follows the black path, has to travel an extra 300 meters to put it out of phase with the gray wave. And so in order to travel an extra 300 meters, this distance has to be 150 meters. That is B, number 17. Consider the superposition of these two waves. Which of the choices represents the interference pattern? Let's see, that cancels. This adds up. That part cancels and that part cancels, but you add up there. So you get 2 big bumps. That's C. Melting point of water is 0 degrees Celsius. That is 273 Kelvin. You'll use this table in the next 2 questions. Cylindrical steel sleeve is to be shrink fitted over a steel shaft whose diameter is 3.2030 at 0 degrees Celsius. Okay, so you're trying, and then that gives the diameter of the sleeve and the temperature. You want to heat up the sleeve so it fits over the shaft. Let's just pick out what we know. L0, that's for the sleeve, because that's really what we're heating up, is 3.186 centimeters. Delta L is 3.2030 minus 3.186. And that is 0.017 centimeters. T initial is 0, and we want to know what is T final. And this is steel, so this is our alpha value that we're concerned with. So we just say delta L equals L naught alpha delta T. And since T naught is 0, we can just say delta T is equal to T final, because delta T is T final minus T initial, but T initial is 0. So we want to look for T final. It's L naught alpha over delta L. Let's see, that gives me 3.186 times 11 times 10 to the minus 6 over delta L, which is 0.017. Notice I didn't have to convert any units because those centimeters cancel out. And I get oh, actually, I'm sorry. I had another mistake here. So I'm looking for T final. So it should be the inverse of this. the inverse. I just had an algebra mistake. T final is actually delta L over L naught alpha, and that is 485.1 degrees Celsius. So that is A. Number 20 is A. Now if you get the wrong L naught, that is if you put like 3.2030 for L naught, that's not the right initial length. If you put that in though, you'd get a slightly different answer of this 482.5, but that would not be correct. Or you have a copper rod that is stuck in a concrete block. Here's your concrete block. Here's your copper rod. What can you do? Well, if you heat it up, copper has a bigger coefficient of linear expansion, so if you heat it up, the copper gets bigger faster than the hole in the concrete. So this does not work. Obviously, if you just heat the copper rod, that doesn't work. If you cool the concrete block alone, the concrete block just gets smaller. The hole in the block gets smaller. So it must be B, that you cool the copper rod and the concrete block at the same time. And you cool it because the copper rod gets smaller faster than the concrete block, and that would be able to take it out. Now in practice you wouldn't really be able to cool it because you'd have to cool it a lot in order for this to work, but in theory it should work. What's the equivalent of 70 degrees Fahrenheit? Well, you can work through this, but you should also just know that room temperature was about 70 degrees Fahrenheit. It's about 20 degrees Celsius, so just knowing that's D. See, I have a cylinder with a movable piston. This is my initial temperature, T1. This is V1, and this is P1. What is its final temperature? That is, what is T2 if we have this final volume, V2 and P2. All right, well, I have PV equals nRT, and PV nRT. This is 1, 1, 1, 1. 2, 2. I can just divide these two equations. The N and the R cancel. And I'm looking for the final temperature. This is T1. So if I solve this for T2, I get T2 equals... I get T2 is equal to T1 times P2V2 over P1V1. There are different ways you can work through this, and you can find N and then go back and find what is the final temperature, but this is probably the easiest. I worked this way in the homework. So just putting in my values, 296, P2 is 0.8 times 10 to the 5th. V2 was 0.7 cubic meters over P1 is 1.2 times 10 to the 5th times V1, which is 1.3. I'm just going to get rid of these 10 to the 5th to make the calculation a little easier. So I'm looking at 296 times 0.8 times 0.7 divided by 1.2 and divided by 1.3. Let's see, I get 106 Kelvin, so it's A. Alright, two identical cylinders of the same pressure contain the same gas. If A contains 3 times as much, which has the higher temperature? Well, PV is equal to nRT. Alright, if N goes up, that means that T goes down. So A has more gas, so it has a lower temperature, so that must be B has the higher temperature. The SI unit for temperature, the Kelvin, is based on which of these? It's not the freezing. It's B. Neither of these is really mean anything. What is the smallest unit of temperature? A degree Kelvin, a Celsius, or a Fahrenheit? Remember, Celsius and Kelvin are the same. Celsius, there are 100 degrees between freezing and boiling. And Fahrenheit, there are 200 and odd degrees between, or 180 between freezing and boiling. So it must be Fahrenheit because there are more degrees between freezing and boiling. It's the smallest. And this is version A.